So f prime of x is a function. So f prime of x is this new function, but it's only going to exist whenever f prime of some specific value does, right? Remember, f prime of a is a limit. So that limit exists, and if the limit exists and is going to spit something out, then the derivative will be whatever it spits out. So the question is this. We might want a good way to talk about those times. So if the limit exists, f is said to be differentiable. That's a big word. So if the limit exists, f is said to be differentiable. D-I-F-F-E-R-E-N-T-I-A-B-L-E. At x equals a. Or if the limit exists for all points on an interval, f is differentiable on that interval. This is pretty common for us. Like we'll invent some language and then we'll talk about, okay, well, it's defined this way at a point, and if it's that way and is cool for all of the points, then we'll just use the same language over the interval. And if it's that way for all of the points that you could possibly be curious about, then we could just so if all of the whole domain is differentiable, then we'll just say that the function is differentiable. The good news is that almost all of the functions that we're familiar with are differentiable functions. The derivatives will exist for all of the values that you could possibly plug into the function. If you plug a number in, then a derivative will spit out. Right? There will be some slope to the curve there. That raises a question. What would it look like if f were not differentiable? Right? So the derivative does not exist. Right? Limit as h goes to 0 of f of a plus h minus f of a all over h does not exist. Right? Then, right? It will not be differentiable. It would not spit out a number. Can anybody think of behavior for a function that would mean that we couldn't find its derivative? That it wouldn't have a tangent slope?
No rate of change.
Right, so no rate of change in terms of like it's not changing, or no rate of change is in it's...
As in like f of 0?
So f of 0, if f prime of x were 0, then we might know what that looks like. The derivative would be 0, and so it would just be constant.
You have nothing to change on it.
That's fine. I have a way of talking about that. The slope is 0. So if it were flat, then if the function were flat, it's not changing, and I can say that the derivative is 0. Okay? So I mean, there is a slope. Yeah.
The slope of the graph is vertical.
Yeah. So vertical slopes don't exist though. So horizontal slopes are okay, right? But vertical slopes, right? So say for instance here, right? There might be a point on this graph where the curve kind of goes vertical, just for an instance. Okay? So vertical slopes do not exist. Okay? So that's definitely going to be a time where the derivative won't exist at that time. So vertical places in the graph are not good. Yeah.
What about like a sideways parabola where there'd be two different slopes?
All right, so that wouldn't be a function.
Right.
So we're not going to consider the derivatives of that. Right? So in general, right now, we're going to be thinking about functions being, we're thinking about functions and the derivatives of those functions. So if we're not putting a function in, then the derivative will just think of that likewise. That would kind of create an issue though, right? So if you were to think about a sideways parabola, right? The problem with that is it's not a function. You plug in one x value and you get two y values, right? So for the derivative, if you plug in one x value, you're going to get two slopes, one up here and one down here. So the derivative would also not be a function. And at least for now, we'd like to kind of think about functions. We can think about things that aren't functions once we've kind of wrangled the easier stuff. When do limits not exist? Right? So we're talking now about derivatives not existing, but a derivative is defined using a limit. So what could happen that would make a limit not exist? Yeah, right? So if it looked like a different number on the left than the right, and here we're talking about slope, right? So if the slope on the left was different than on the right, then the limit wouldn't exist. So something like this would be bad, a V type of shape, because maybe the slope over here, it looks like -1, -1, -1, -1, -1, and then the slope over here looks like 1, 1, 1, 1, 1, 1, right? Straight lines always have the same slope. So quick changes in direction. You might think of these as corners. Sometimes they're called cusps. Yeah.
That doesn't have anything to do with whether or not it has continuity, correct?
Correct. So just because it changes direction really quickly, it might still be continuous.
That still has continuity.
Yeah.
Okay.
But if the function were discontinuous, then we would also not talk about the slope at that point. So that would be another time when the derivative wouldn't exist. Right, so f is discontinuous.
If there's a hole in the graph, is it still discontinuous then?
Yeah. So if there's a hole, if there's an asymptote, there's a jump, which jumps look like this, right? It picks up and then drops back down somewhere else.
In that case, we don't have to talk about limits either, correct?
So the limit would not exist for the function here, and the limit is also not going to exist for this derivative. But we might talk about one-sided limits here. So I might talk about the limit from the left or the limit from the right. Because those would give me information about the function. It would kind of tell me like, oh, it's headed toward 3 on the left side and it's headed toward 2 on the right side. It gives me an algebraic way of talking about this picture. Right? A lot of math is like, okay, I have this picture. How can I describe it using language and symbols? Right? And that can be very difficult, and it can require very specific definitions. Right? We found that when we played Zendo on day 1, right? It was kind of hard to talk about what these little structures looked like. Right? Oh, I've built this thing. What does it look like? Oh, well, it's got 3 pyramids in it. What color are they? How big are they? How are they related to one another? Right? And we had to invent language, right? Upright or flat or large or medium or small. Right? So language, super important. And that's why we're coming up with things now like differentiable or non-differentiable. All right, so these are the 3 main times that we might be worried about. So this is these are the times where a function will not be differentiable. Other times, it's pretty great.